On the previous page, we saw where HX could add across the double bond of an alkene. In the first step, a new CH bond was formed. But what if, instead of X- bonding to the right-hand carbon in the second step, another alkene molecule took its place? Just like X-, the alkene is a Lewis base, with the carbon-carbon double bond able to provide a pair of electrons to form a new covalent bond. We diagram it like this. The result would be the formation of a new carbon-carbon bond with the positive formal charge migrating to the right-hand carbon of what was the second molecule. Imagine another alkene molecule approaching, forming another new carbon-carbon bond. The result of this process is the formation of a polymer. In this animation, we have an alkene, double bond between the two black carbon atoms, and on the left carbon atom we have two hydrogens in light blue, and on the right-hand carbon we have two generic R groups in gray. And we're going to bring, instead of an HX, simply an H+ to form a new carbon-hydrogen bond. Let's watch what happens. Double bond provides two electrons for the new carbon-hydrogen bond. Let's stop it there. Notice we've gone from trigonal planar to tetrahedral geometry, and now the positive charge has moved to the right-hand carbon, and we bring up another alkene, which can form a new carbon-carbon bond. Again, shape change at the carbon, another alkene comes up, shape change at the carbon, the positive charge migrates out to the end, and this can continue on until we get a polymer. And if we look closely at the polymer that's formed, along the carbon backbone, we have alternating carbons with Cr2 and CH2. Carbon with two R groups, carbon with two hydrogens, carbon with two Rs, carbon with two hydrogens, two Rs, two hydrogens, and so on. So there's actually a regular arrangement of the atoms in this polymer. We have suggested that these polymers alternate carbons with the two hydrogens and two of something else. The properties of the polymers can be manipulated by manipulating those other positions, as well as manipulating the manufacturing conditions. Notice in the picture there are N of these repeating units. N can be manipulated from hundreds to hundreds of thousands. If, in the two remaining positions, one were hydrogen and the other were a six-membered benzene ring, we would have polystyrene. Polystyrene can be processed to be very hard, or if it's processed with a gas like pentane present, which is then driven off after the polymerization, we have styrofoam, which is light and airy. If one of the positions is hydrogen and the other is chlorine, we have polyvinyl chloride, or PVC, which is used in pipes. If one of the positions is hydrogen and the other is CH3, we have polypropylene, used in many containers. If both remaining positions are occupied by hydrogen, we have polyethylene. Depending on the processing conditions, we can get high-density polyethylene or low-density polyethylene, which have different recycling symbols. If all four positions around the two carbon atoms are occupied by fluorine atoms, we end up with Teflon, like what you have in frying pans. It's amazing to imagine that this very simple type of addition reaction, adding across the double bond of an alkene, which we can understand and diagram, is the basis for a multi-billion-dollar industry.